years at Google. It's going to do that. Okay. Oh, we're
Right here.
Hmm?
You can hold this.
Oh, I'm gonna use the phone. Okay,
Yeah.
Gotcha. So hopefully everybody can hear me. Welcome and thanks for coming to this presentation. I hope I didn't scare anybody with the title. My name is Ray Cromwell. As mentioned, I am a Zoogler of approximately 15 years. The last 2 to 3 years I've been working on AI, particularly AI safety at Google up until January. And yeah, I was basically starting to work on startup ideas. And I was looking around, I was trying to train some data up in the renewable energy market on predicting like energy demand stuff. And I started to use transformers because transformers are hot. Everyone's using transformers to solve everything. And I kind of ran into a problem, which was I wasn't getting very good results. So I started doing some searching. I was like, well, is anyone else doing machine learning on transformers on small data sets? And it turns out this paper turned up. And I was like, okay, what did they do differently to fix this? So the question is like, why are transformers hungry, so hungry for data? And that's kind of like the topic of this conversation today. It's not so much the vision transformer paper. What we're going to take away from looking at this paper is the methodologies and techniques they use to actually like tweak their transformer to make it perform better on small amounts of data. And so that's what I hope the real takeaway is, not for you guys to learn very deep into vision transformers, because honestly, I'm not very deep into vision transformers. So I'm kind of just as much of a neophyte as most people in the audience. Next slide. So question is, what's a vision transformer? Well, it's almost identical to a text transformer. So like transformers were mainly invented for language translation tasks. Like let's match up like English with, French or German. And so they're really, really good at that. You cut up a sentence into a sequence of words, you feed it into this transformer. You sort of do this thing where you vectorize the words first, you embed them into a space. But the key thing is the transformer learns to figure out like sort of the meaning of the words and how to translate them via this attention mechanism. Well, vision transformers basically did the same thing. Someone just took an image, they cut it up into a sequence of tiles, in this case, 16 by 16 pixel tiles, and it just flatten them into like a one-dimensional vector value. So if you get 16 by 16 pixels, you've got 256 values. So it's just a 256 element vector. And it just fed it into the transformer like it's a bunch of words. Next slide. So this is an example. Typically in the transformer like picture like this, the bottom row here where you see these images would be words like Mary had a little lamb. Here it's just basically slices of this image that's been divided into 9 tiles on the left. We okay?
Yeah.
Okay. Oh, okay. Yeah. So basically, we've taken an image, we've sliced it up into 16 by 16 tiles, and we just fed it into a off-the-shelf transformer with no changes, as if they were words. Next slide. And shockingly, it works. So unlike the other successful model, convolutional neural networks, this actually makes very little assumptions about the input data. Sorry. Transformers make very little assumptions about the input data. Convolutional neural networks make a lot of assumptions, like pixels are in a 2D arrangement, nearby pixels basically, have some relation to one another, and so on. And like even taking 2-dimensional stuff and flattening it into 1 dimension and feeding it into the transformer, it still figures out like, do these group of numbers that look like a wheel and these other far away things that look like maybe like a spoiler is just a Formula One scene, and it will end up classifying it. It's pretty amazing. Next slide. But there is a big downside when you're not able to like kind of pre-program sort of like assumptions about your data shape, like it's 2-dimensional. And that is the transformer has to learn the stuff that like the convolutional networks basically kind of had baked in, like, there's 2-dimensional locality of pixels. So it can't assume it has to learn it. So they say that previous systems like convolutional neural networks leveraged like 2 things, 2 inductive biases, they would say, locality and translational equivariance. And if you train, vision transformers on small data sets, they trail the performance of convolutional neural networks by substantially. But if you scale up to like 300 million images, it basically, this is a quote from the paper, it basically beats convolutional neural networks. So the bottom line is you can get better than CNN performance, but you require lots more data. Next slide. So I mentioned inductive bias. So if you haven't heard this term before, I'll explain. You fly to Switzerland, you go out into like the park and you or the forest, and you see this, a cow with a cowbell. What can you infer from this image, this observation? Next slide. Well, you could make many theories about this. You could say all cows have bells. You could infer all spotted cows have bells, or all cows in Switzerland have bells. Or maybe you would just take the minimum and say, well, at least I know there are cows in Switzerland. That's my hypothesis. So all the data that you collected fits all of these hypotheses. So how do you choose which one to pick? Next slide. Here's another example. You have two data points, x1, x0 and x1. Now, you know from basic algebra, you can put a line, a parabola, a cubic through 2 points. You can put many, many curves through that. Now, if I collect one more point, x2, which of these three models should I choose? They all kind of fit the data a little bit, right? So how do you decide? So one of the most famous inductive biases, you already know, Occam's razor. You know, the simplest explanation is the best. So, you know, in the original case I showed you with the cows, the simplest theory is Switzerland has cows. Not all cows in Switzerland have bells, right? Or that maybe if you see a bunch of data and it looks linear, let's just assume it's linear and go with that, right? So those are examples of inductive bias. Okay, so how does this help with vision transformers? How does it make them or help them work with smaller data sets? So, well, the two things that I mentioned earlier is if you pick inductive biases of locality and translational equivariance and try to put those back into the transformer somehow, you'll improve the performance. And so, like, what does locality mean? Well, it basically means that the pixels that are nearby in the input data have some relation. So maybe nearby pixels form edges. Nearby edges at a higher level form shapes. Two shapes that are nearby form objects, and so on, in sort of a hierarchical fashion. Transformer doesn't assume that, but convolutional neural networks do. And translational equivariance is basically just a fancy way of saying that, like, if you shift around the pixels in the image, what neurons can recognize, like in this part of the image, will also be recognized over here. So if I have a bunch of neurons that recognizes like a 45-degree line, up in the top left-hand corner of the image, if I simply like move that over to the bottom right-hand corner, those same neurons will still recognize the 45-degree angle. Now that might seem like obvious, right? But like if you were looking at like a Mercator projection of the Earth and you put like a right angle on the globe, it actually, a 45-degree angle actually won't be 45 degrees at the edges. It'll only be 45 degree at the center of like the Mercator projection. So that's an example of like an assumption that a transformer wouldn't assume, but like basically CNNs do. And so we want to try to put that back into the transformers. Next slide. So how do we put pixel locality back into the transformer? So what they do is well, first let's talk about, previously I mentioned that the image is sliced up into tiles that are non-overlapping. And the problem with this is that two pixels that are nearby that end up in two different tiles lost their relation. So in like when you feed it to the transformer, the two nearby pixels basically end up in different tiles. So some of the interrelation has been lost in the token. If you next slide. So instead, if you basically take the original image and you before you feed the tiles into the transformer, you shift them like in different directions by a little bit, shift them up diagonally, like and all four corners a little bit, and you combine them. Now you've got basically where you had one tile before, you've got 5 tiles, and there's a little bit of overlap now between nearby pixels that would have been like separated in 2 different tokens. And so your new tokens that you're feeding to the transformer are basically like 5 tiles per token, but each set of 5 is really just in the same local area, shifted around a little bit.
But how's that introducing inductive bias and helping?
So what's happening is that when these tiles are fed into the transformer, the first step they have to go through is they have to be projected into an embedded space. So like with words in English, let me see if I can explain this. With words in English, when the transformers like take an English word, they don't just take the English word, let's say apple, right? What they do is they project it into a higher dimensional space, let's say of like 3 different values, a 3-dimensional vector. And the axes of that vector could be like red versus green, small versus big, and like, you know, animal versus vegetable, right? And so it would say like an apple might be like 100%, like 1.0 red on one coordinate. It might be like 1.0 or 0.9, you know, like is a tomato a fruit or a vegetable? Like it will be some percentage of vegetableness, right? And then some percentage of size. And then what the transformer gets is these vectors, which have sort of like meaning captured for the words like in the coordinates of the vector. The same thing happens for the image. Is when you feed these images in, they're projected into a higher dimensional space. So they're not just, the raw pixels don't just go into the transformer. If you go back to a previous slide, you can kind of see one slide previously. You can see that they go into this thing called a linear projection of the flattened patches. So the pixel values are fed into this thing, and this thing feeds it into like a higher dimensional space. And that space then learns like some interrelatedness between the components, right? Because they cluster in high dimensional space. So like, for example, all of the red fruits, if you think of its 3rd dimension being how red it is, if you look in like space, like apples would be clustered with strawberries and so on. So you get sort of a clustering of the meanings. And the same thing happens when you take these patches and you shift them around a little bit. All the ones that kind of share pixels might end up clustered together in this high dimensional space. And so you kind of learn some related things between tiles if they kind of cluster together. But that's kind of that could be a total separate talk about how these embedding spaces or latent spaces work. Maybe we can do that another time. Okay, so shift ahead. Okay, so now there is some 2D pixel adjacency information somehow being learned now, because you've kind of like took the image and like slid it over and like concatenated it together. But the other thing to think about is, more simply, the way I think about it is, we had too little data, and so we just multiplied our data set by 4 or 5. We synthesized more data. We took an image and we shifted it around like 4 times, and so now we've actually expanded our data for free. Basically, that's another way to think of it. Sorry, next slide. Okay, so the other inductive bias thing that we have to fix is, a typical corpus of documents, the total amount of English words in the entire corpus of millions of documents might be like 60,000 English words. And so normally the transformer is just kind of like a giant list. When they tokenize the words into numbers, like this is, the word apple is like word number 2, and, the word car is number 42. They turn them into numbers, right? The space of possible images is much, much, much larger than the number of English words. Like a 16 by 16, that's 256 values, is way more possible variance on tiles than on words. And what happens is the attention mechanism, and I don't understand exactly how this arises, but this is what the paper says. The attention mechanism tends to spread its attention because of this over many, many, many more tokens. So it kind of develops sort of an attention deficit disorder. Think of it that way. Like there's just too much stuff to pay attention to. So the attention mechanism kind of just goes like, well, all right, I'll just pay attention to everything equally. And so you get this like smoothed out effect. So you can see it in the blue graph in the bottom. Is like they're showing like what the output of the attention will be. And that graph is basically like every token compared with every other token for similarity. And it's basically giving you sort of a roughly, they're all the same. You can't really tell which thing to focus on. And by this technique that we're going to get to in the next slide, they get more sharp peaks. And like if you see in the purple thing on the right, after we apply this technique, you get like a sharper focus. Like these 2 words, these 2 tokens are the things like I need to pay attention to, right? So the transformer loses efficiency because of this smoothing problem. Okay, so how do we fix this? There are 2 ways. One way is we do what's called masking self-attention. So if you haven't learned what the attention mechanism is in a transformer, just think of it like this. It's comparing every word in a sentence with every other word in the sentence and computing some relational value between the 2 things. And in this case, even the word it, if you see in this picture, is being compared with it. So it's saying like, my query is it, my query token is it, and the key token I'm trying to see if it matches or not, matches with this value, and it's that little like sort of like a red line there. So what we do with this locality self-attention thing is we set all of those self-attentions, whether it's a word with itself, to negative affinity. So basically the transformer can't use a word with itself. It's like ignore a pixel being compared to itself. So what it does is it forces it to pay more attention to the pixels that's nearby the one that's under that's you're basically looking at. At least that's the explanation, is that it tends to trigger the transformer to look at the nearby pixels instead of focusing a lot on your own. Because like if you compare yourself to yourself, you're going to find a lot of similarity you're going to match, right? So you take that out of the thing that you're searching for. Next slide. So the other thing is what's called learnable temperature. I don't know how many people know what temperature is in machine learning, but basically it's what's called a hyperparameter, and it's usually used to sort of adjust, let's say, how creative the output of your network is. Think of it that way. And so what you're seeing here on the left is a typical MNIST. MNIST is this famous machine learning benchmark where it's like tens of thousands of handwritten digits from 0 to 9, and you're trying to recognize a handwritten digit. Is it a 0, 1, 2, 3, or a 9? And in the top bar graph where it says logits, you can see that 9 is the most probable. It's the highest one. It's like 60%. However, the other ones are close. So it's like kind of saying like, but like a 7, it's like 50% a 7 and only 60% a 9. Which one do I choose? And what you do is when you apply temperature, you boost the one that's the highest number up, and you press down all of the other values that are not close, not the maximum. And so it gives you a much like sharper focus. Like if you look at the bottom distribution, well, obviously it's a 9, right? Because all the other numbers have been pushed down, all the other predictions. And so in general, the lower the temperature, the more sharp your output, the more confident, I guess you could say, your output prediction is. And the more you raise the temperature, the more things kind of even out. If you look at the bar graph on the right. Now, why would you even raise the temperature, for example? That would be a question, right? Well, let's say you're doing generative imagery like Midjourney or something, right? You want to generate like 4 or 5 different images. You want the AI to be like creative, right? To sort of like imagine more things. If you set the temperature like really low, then you're always going to get the same image. Like it's going to always do the same prediction every time. But if you kind of like increase the temperature, you kind of like increase the randomness. And so you get more creative outputs. And so that's one reason why you might want to do that. But this is kind of bad for the vision transformer case. We want really good predictions. We don't want sort of random predictions. We want to know we're classifying this thing. Tell me if it's a car. I want to know it's a car. And so you want the temperature to be low. Okay, so I explained the smoothing problem where all these weights would tend to be like smoothed out and you wouldn't know which is which. So you want to lower the temperature so like one of them like rises to the top. Normally though, you have to manually do that when you're doing machine learning. You have to set the hyperparameter beforehand. Go like, all right, I'm going to make this temperature 0.5. I run it, I pay my money to GCP, because I burned up TPU hours or GPU hours, and then it comes out and it doesn't work, and I have to adjust the temperature again. So you're fiddling around to find out. Next slide. What they do in this paper is they say, well, like let's make temperature a learnable parameter. So you add it as another parameter to your network, and now the network actually learns the temperature parameter. And when they did these experiments, the learned parameter actually tends to be a lot lower than the one a human being would pick as a hyperparameter. And so it led to sharper distributions. So it tended to actually give like better accuracy by like basically, yeah, question.
Wait, there's a question on Zoom.
Yeah.
Why would LSA benefit all transformers versus just vision transformer? That's why I run these.
It's a very good question. It might actually benefit all transformers if there's more locality in the data. Like, I think, so this is just me thinking out loud because I really don't know the answer to this, but like today's transformers, people are making huge, larger and larger context windows. Like I think Anthropic's cloud, they just went up to like 100,000 tokens now, right? And so like their locality doesn't seem like that important because like they're expecting the attention to go back like 100,000 tokens. So it's looking at like a lot of stuff. So if you tended to force it to look at like stuff that's closer to the the query that's under evaluation, maybe you don't need such a large token window. You're just wasting computation. So but that's just kind of like me making it up on the fly. I really have to. It's a good question, and after this, I'll try to look it up and see. Next slide. Okay, so what are the results? So this is one slice of the results. There's a lot more out there, but the top line is the normal vision transformer, off the shelf, no changes, right out of the textbook. And on Tiny ImageNet, it's 57% accuracy, which actually is not that great. I mean, it's almost like flipping a coin, right? If you think about it. The LVIT is the vision transformer, but with the local self-awareness and learn temperature stuff I just talked about. The SVIT is the one with the patch shifting. And you can see that individually, the LVIT goes from 57 to 58.50, so it adds about 1.5% accuracy. The shifted patch tokenization goes from 57 to 60.67, so it's about 3.5% improvement. And then the bottom one is like both of them together, and you get like about a 4% improvement. So that might not seem like much. Let's look at the next slide. So this is comparing it versus ResNet 56, which is kind of like the classic convolutional neural net that's basically been used a lot. And you can see on the far right on Tiny ImageNet, it actually only does 58.77%, and the SLVIT is doing 61%. So we're beating convolutional neural networks on a tiny data set. But what's more interesting to me when I looked at this was, look at the throughput in the flops. The transformer is almost double the number of images a second being processed, and like less than half the computation, the flops. So it's not only beating the convolutional neural network, but it's actually like doing it at like half the computational power, which to me says that this is like a worthwhile technique to look into. Next slide. So in summary, what I kind of wanted people to get out of this is not the vision transformer and how they work in particular, but basically sort of the general approach that like transformers are like super flexible. They don't have a lot of like assumptions about the data input. So they're very general. They can do almost anything. But the penalty for that is basically they require more data. And if you're a small startup and you tend to have less data, or you can't afford to run on a lot of data, it just costs a lot of money to process a big data set. But you can kind of overcome this. And the general approach is to look at your data and is there anything about your data that you can figure out an inductive bias for? Like, is it locally structured? Maybe it's 2D, 3D. Maybe it's time series data. So I was actually working with time series data, like predicting renewable energy demand and supply versus like weather. And there's seasonality to the data. So there's not locality, but there's like a sort of a long-term locality, like, you know, every August something happens, right? So if you have like a 20-year data set, there's an inductive bias, but it's seasonality, right? So if you can figure out one of these biases, you can perhaps improve your performance on your small data sets. And of course, shifting inputs around can synthesize new data. Masking attention is another trick, and the learnable temperature is the other one I showed you. So yeah, that's basically it. It's like, what will you figure out for your applications?
We got a question on Zoom.
Yeah.
Can vision transformer models be fine-tuned to a specific task the same way that other vision models can?
Yes, they can. I think that actually there's an example of this. There's a Medformer, I think it's called. There's a medical imaging, like radiology one, where they've taken like an already existing transformer, vision transformer that's been trained on like a diverse data set, and they fine-tuned it further with like medical, like anatomy, or like maybe like x-rays and things like that. If I can find it, I will send it in chat or like post it to the mailing list or something.
I think I read something on that, where it actually was trained for skin cancer, that you put a ruler next to the
Yes. Yeah, like it actually learned the wrong thing. He's right. In one of the examples, basically, they were like measuring moles or something like that. And basically, it was like, is this picture of skin, of someone's skin, a picture of skin cancer or not? And the problem was that every one of the pictures with cancer, there was like a little ruler next to it where the doctor was measuring how big the mole was. And in the ones where there was no cancer, there was no ruler. And actually, it turned out that what the transformer actually learned was rulers. Rulers equals cancer. That's actually a great sort of caveat you have to think about. So if you go to the next slide,
that's an example of bad inductive bias.
Yes.
There's good index to bias and bad index.
Exactly. So if there's a link that's sent out with the presentation and you're new to transformers or new to visual transformers or inductive bias or temperatures, I put what I feel or like some of the resources that I myself use to learn or to brush up on in this paper. And some of these I find are quite good for explaining things. And at the very bottom, there's a GitHub link to an actual, I believe it's PyTorch. I believe it's there's a PyTorch implementation of the SLVIT that you saw here today. So that's all I got. If there's any other questions,